What's up everyone, it's John Kim here at IB The Top. I'm your math instructor, and today we'll be talking about 7 topics to get you that 7 in your math IA and EE. So fasten your seatbelts everyone, let's get on this rocket to get that 7. But Houston, we seem to have a minor problem over here. We're trying to describe the orientation of our rocket, but we're all using these terms like yaw, pitch, and roll, and I have no idea what that means. Well, let's find out what that is. Well, actually, this is when we're using geometric transformations using vectors and matrices. So if you see the 3 matrices right here, what's happening is we're going to multiply these matrices to a direction vector, and that's going to apply appropriate transformations, be it a reflection, rotation, translation. So we're not just limiting ourselves to rockets. For physics fans out there, we can talk about rotating frames of references. So maybe in an inclined plane problem, we might want to talk about switching up our frames of reference from XYZ to a slightly tilted XYZ plane. For image processing, we might take this picture of Einstein, we want to stretch it, compress it, rotate it, reflect it, whatever we want. We're going to apply these vector transformations to pixels. So if you're interested in any of these topics I've just talked about, topic 1 is just for you. Secondly, let's talk about the coupon collector's problem. I'm sure you all heard about the Pokemon bread. You buy 1 bread, you get a free Pokemon sticker, and the goal is to collect all of them. So one might ask, what's the average effort? How many purchases of this bread would you need to make sure that we collect all 151 Pokemon? So this is a step up from the normal probability and statistics concepts you do in your IB syllabus, but we're also taking a look at, say, linearity of expectations or Markov's inequality, and a brief sneak peek into the derivations are shown right here. And you could extend this topic by asking, if you were to figure out what price you would sell for your very rare coupon, how much would you charge? Should that price reflect the effort of countless breads you should go through to get that coupon? So if you're interested in hoarding all of these Pokemon stickers, here's a fun topic. Thirdly, we have the knapsack problem. So let's say you're on a treasure hunt. So you have this bag and you're Indiana Jones, you raid this tomb, you want to make sure to fill up that bag to get maximum value as much as possible. So you have limited weight or carrying capacity, but you want higher value. So this knapsack problem, which is very popular in the field of mathematics and optimization, can be extended to other concepts. If you have a sports team, how many players are you going to get? What are you going to pay them? And how are their performance indices going to make sure that you have the best team? We have a heat map of the US stock market here. We have Amazon, Microsoft, Apple. We have all these different stocks that have different returns, profits, and different risks. So if you were to fix our level of risk, how can we maximize the returns? If you want a certain return, how can we fix that return with minimal risk? So a brief outline of the formulation is shown here. We want to maximize this objective function while making sure that we abide by these constraints expressed as a bunch of equalities and inequalities. So if you're interested in how we can live life to the fullest by making the best choices out there, whether be it having the best sports team, having the best, most profitable portfolio, this topic would be for you. The next topic, all about cues. So what are cues? Well, they're basically synonymous for lines. If you've been to a sandwich parlor, you may have seen one employee lay out the bread, toast the bread, another employee put the meat and cheese, and they pass the bread on so that another person can add the vegetables and the sauce. But you'll notice that the process isn't smooth all the time. There may be some holdups. So maybe the person adding vegetables is pretty slow, so there's a large stack of unfinished sandwiches where he's working. So we call this the bottleneck. And it's not just for sandwich parlors. We can extend this concept to factories, production lines, theme parks, waiting lines at banks, grocery stores. So mathematicians analyze how queues form and how we can improve the customer experience whenever these queues form. So we have Little's Law that talks about works in progress, throughput, cycle time. So all these matrices, performance metrics, help us analyze how a line is doing. So the complex derivation you see right here is an example of steady state analysis. So we would be calculating things like, what's the probability that the line is empty? What's the probability that there's one person in the line? what's the expected number of average customers waiting in the line, or what's the expected waiting time per customer. So all of these would be very important if you're trying to streamline processes. So if you're into economics, business, this might be for you. The next topic, I chose an easy one. You're probably familiar with these topics. It's optimization for various geometric shapes. So if you were to have a cylindrical can and you want to contain a certain amount of volume with minimal surface packaging, what kind of dimensions would you go for? So we might express volume and surface area in terms of radius, height, and we can apply differentiation and single variable calculus to find out that maybe the radius should be half the length of height, or height should be twice the radius. But we may have other situations where we're trying to optimize, but we're not only dealing with one variable, but more than 2, 3, basically multivariable calculus. So when we're dealing with multivariable optimization, what comes in handy is the Lagrange multipliers concept. So one example is the Cobb-Douglas function right here. So L stands for labor, K stands for capital. So if we have this function, a product of L and K, and we want to select the right balance of L and K to maximize productivity, what would we do? The stuff you did in IB mainly focused on what happens if there's only one variable, but we would extend that concept to more than 2, 3, 4 variables at a time. So Lagrange multipliers, this ties in with partial differentiation, vector calculus, linear algebra, and all that. So this topic, if you want to keep it easy, it'll stay that way. But if you want to dive deeper out of your own will, or because your teacher says add more math, we can always extend the whole playing field. We can level the playing field. Up next, we have inventory management, the Wagner-Witten model. So this also would cater to the interests of economics and business students. So here's a problem. Let's say we know the demand forecast for the next 10 weeks. And we have the option of producing each week or producing a large stockpile and maintaining an inventory. So one possible solution, if you see in the first table at the top, is producing week by week, lot for lot. So if the first week requires, say, 20 products, you would make 20. If the next week requires 50 or 30 products, you would make the bare minimum of what is needed. So the advantage of this would be that you would keep inventory costs low, but that means you're setting up production very frequently, so this would lead to high production costs. The alternative would be to produce a very large stockpile at the beginning and make sure that your stockpile lasts throughout the next 10 weeks. So each of these choices have their own advantages and disadvantages. We're trying to mathematically figure out what the optimal course of action is. So this topic actually can be tied in to shortest route finding or shortest path finding. So if you were to talk about, we're going from node 1 to node 5 through these different arcs, and each arcs have a different cost. So this problem would boil down to how can you get from point A to point B while taking the path that would lead to minimal total costs. The final topic is arts and crafts on math steroids. So who says math can't be beautiful? If you're interested in art but also interested in mathematics, this topic is just for you. So if you're using Photoshop or these Illustrator tools, you may have heard of terms like Bezier curves. Well, Bezier curves are based on the concept of envelopes. So these equations right here, they're actually envelope conditions. So for instance, if you have a family of lines, so you see a bunch of red lines that have different slopes, we can connect their envelopes to produce a curve. So we can do this for more and more complicated shapes to produce more sophisticated, maybe snowflakes, cardioids, and all these different continuous curves. So I won't go too much into this, but here's an option, right? So if you're interested in art and maths, this topic might interest you as well. So now that we've taken a brief look at potential topics other people have done in the past, let's choose the right topic for you. So here's my take on what makes a good IA or EE. There should be a lot of personal engagement. There should be, it should reflect the student's curiosity and interests. And there should be use of proper mathematics, rigorous mathematics. So the level of mathematics shouldn't be too easy. It should either be in line with the IB syllabus or it should go above and beyond that. And lastly, we also want to make sure that whatever you're doing is consistent with an aim. Have you sufficiently defined a clear, well-structured problem? And are you doing everything you can to answer that question without straying too much from it? And once we have this good topic, I believe we need to demonstrate our understanding through coherent exploration. So coherent exploration, in my opinion, is supported by the three pillars. The three pillars being presentation, communication, and organization. And lastly, we want to make sure to have a lot of critical reflection into this. So we'll first ask ourselves, was this a valid topic? Were my initial assumptions correct? Did I do everything I could to answer my question? Or were there some clear limitations in answering this research question? So I want you to think about what makes a good topic and how we can bring that good topic to light when you're trying to get into this IA and EE. Before we leave, let me just emphasize once more why it's important for you to have the right topic for your assessments. Albert Einstein once said, if he had an hour to solve a problem, he would spend the first 55 minutes defining the problem and the remaining 5 minutes solving it. This just goes to show why it's important for you guys to choose the right topic for your IA and EE. There is a positive feedback loop between a good topic and a proper follow-up writing. So only by choosing the right topic for you will you set an appropriate scope and enable proper, sufficient exploration through clarity in your logic and calculations. And once you have your good topic, that topic is nothing unless you have the proper write-up to back it up. So a good write-up means you're doing your due diligence. Don't be lazy in researching, writing, deriving, and making calculations, because only then will you be able to communicate your findings and understanding to your reader, and only then will your reader know the beauty behind your topic and give you a high score on your IA and EE. So thanks for tuning in. It was a pleasure giving this brief workshop on the IA and EE. This was John, and I hope to see you in the near future. Best of luck, everyone.